Um, right. We're going to get to some of this stuff here. The first homework problem for next week is called Five Lemma. And perhaps you see what it's called, five. It's got five modules across. So you've got a commutative diagram with exact rows. What do I mean by that? Commutative diagram means if you start anywhere in here and you go this way, it's the same as going this way when you compose the function. So you get the same answers going any time that you want. And of course, the exactness means the image of this is equal to the kernel of this, the image of this is the kernel of this, etc. Right? So if you have the following commutative diagram, bar module homomorphisms with exact rows, both of these statements are true. You only need to prove one of them. Just pick one. I don't care which one you prove. Just tell me which one you're proving and prove it. If G2 and G4, if these two animals here are onto, and G5 is 1 to 1, then G3 is onto. Right? So onto 1 to 1 means that middle one's also onto. And the dual result is if these two are 1 to 1 and this one is onto, then the middle one is 1 to 1. And it's a diagram chase, and it's a lot of fun. So I'm going to give you an example of how to do some of this. I'm going to do the short five lemma for you. The 3x3 lemma, reminds me of the Hollywood Squares. This is kind of a fun one. I'm going to do the dual case of this actually in class. What I want you to do is show. So again, you've got the same situation. I was too lazy to write in maps, but these are the columns of these are all exact. So the vertical columns are short exact sequences. And if the top two rows are exact, then the bottom row is exact. The dual result is if the columns are exact and the bottom two rows are exact, then the top is exact. And I'll actually prove that in class, and it'll kind of get the idea, I think. The next one's the snake lemma. How many of you have heard of this? No, snake lemma. This is actually very important along the algebra. So here again, we've got a commutative diagram with exact rows. So going in any direction, you get the same thing. This means image of F1 is the kernel of F2, and it means F2 is onto, right? H1 is 1 to 1, and the image of H1 is the kernel of H2. Show that you have an exact sequence from the kernel of G1, kernel of G2, kernel of G3, and then the co-kernel of G1, co-kernel of G2, co-kernel of G3. Now let me recall for you, the kernel of G1 is just everything goes to 0, kernel of G2, and so forth. Anybody remember what the co-kernel is? The co-kernel of G1 is this B1 modulo the image of G1. And this is B2 modulo the image of G2. So these are all functions. The snake is this thing that connects it, right? So that's kind of the funny. No, I didn't tell you what the maps are, so I think the maps are kind of obvious. When you get into the meat of it, you'll see how this map works. This one's the interesting, because you actually go from the kernel of G3, so you go from something that goes to 0 here into the co-kernel, into something over here of the form B1 modulo the image of G1. And that's how you snake it. You got to snake your way back over here, right? Now, how many of you are movie buffs? I like movies. If you have trouble with the snake lemma, there's a movie from 1980, I believe, called It's My Turn, starring Michael Douglas and Jill Clayburgh. It's about a math professor. Jill Clayburgh plays a math professor. I think it's going through a bit of a crisis in her life. And so she hooks up with Michael Douglas, who's an ex-baseball player. At the beginning of the movie, she's a math professor. She very quickly, but pretty well, explains the way the snake lemma works. So if you're having trouble, you can look up It's My Turn. But if you cheat and do that, your punishment is you have to watch the whole movie. So think about it first. Finally, an R module S is said to be simple if it's only submodules are itself in zero. Show that any simple R module is cyclic. And this is the definition, cyclic, that is, it's in the form R times A for some A and S. And then characterize all R module homomorphism from S to S, where S is a simple R module. Think about kernels and images because you've got a limited number of possibilities. Okay, any questions? All right. So the last time we talked about short exact sequences. A short exact sequence, if this is a short exact sequence, then F is 1, 1, because you have to be exact here. The image of this is 0, so let's call that. P is onto. The image of G must be the kernel of this, the kernel is all C. So G is onto, and the image of F is equal to kernel of G. It's going to turn out that any exact sequence can be obtained by splicing together short exact sequences. And that's going to be a homework problem for you later. And we looked at some examples, including some examples of sequences that can be run in the other direction. We're going to talk about that more extensively later. Let me give you the proposition. And this is all, I'm not going to prove this, I'm going to prove a corollary to it, and you'll see why I'm going to prove it. 6.44. This is called Five Lemma. In your homework, so I'll just write it down here for completeness. If you have the following diagram, right. So here also point out its next. So F1, F2, F3, F4, H1, H2, H3, 4, 4, 2. Okay. Suppose this is a commutative diagram with exact terms. Then if G2 and G4 are onto, and I think G5 is 1 to 1. Yeah. And number 2, if G2, G4 are 1 to 1, and G1 is onto, then G3 is 1 to 1. So notice there's a symmetry here, right? These two being onto and this 1 to 1 gives onto in the middle. These two being 1 to 1 and this one onto gives 1 to 1 in the middle, right? And this is what you prove for at least half of it. Let me give you a corollary, which we'll discuss why this follows pretty much immediately from Five Lemma, but I'm going to prove the corollary not using previous. Now, give you an idea about how these things go. It's called short five. Um, again, we have following community diagram with exact rows. Here's the conclusion of the short five. If G1, G3 are onto, so is G2, 2, if G1, G3 are 1 to 1, so is G2. And I can't resist if G1, G3 are isomorphisms, so is right. Notice the 3 follows immediately from 1 and 2, correct? Now, tell me why this follows 5 lemma. Right. Well, the only other condition you needed in 5 lemma, I mean, this specializes in the case where A1, A5, B1, and B5 are all 0. And the vertical maps here are both the 0 map and the identity, right? Because it's on the 0 module. So clearly, these are both 1 to 1 and onto. So that condition is superfluous here, right? So this follows immediately from that. I ain't gonna do it that way though. I'm going to do a formal diagram case. So I'm gonna prove short 5 first principles. Just 1 and 2. The reason why I asked you only to do a limited number of these diagram chases are about the most fun that you can have sober with this kind of thing. But it can be kind of obnoxious to write down. Okay. Let's prove. First, we'll prove 1. Suppose G1, G3 are on. Myself. Colored chart. Okay. What do we want to do? We know that these 2 are onto. We want to show that this middle one is onto. So let's let V2 be here. Most of what I'm going to do is kind of draw a picture of this, right? Now, I want to show if there's something here that goes to here, right? Well, if I could just do that, it'd be done, but I know nothing about G2, except diagrams. The only thing I can do is push this somewhere through this map. So suppose when I draw this arrow, that means I've applied H2 to get this, right? I push this here and I've got B3, right? Now, what do I know about G3? It's onto, right? So up here somewhere, there's some A3 that goes down there. Great. Huh. What now? Any suggestions? I can go backwards, can't I? Because don't I know that this is onto? Because the top thing is exact. So there's an A2 here. Oh, look at that. So A2 goes to B2, right? Maybe not, right? Here's what I do. If I push this by G2, this goes to, I don't know, X. Maybe it's B2, maybe it's not. I just don't, I don't know yet. Well, what do I know about X? If I push X to the, which makes sense, to the right, where do I get? How come?
It's the diagram views.
That is correct, right? When I look at A2 and do the walk, I go to B3. So when I do the walk this way, no matter what X is, it's gotta walk to B3. Right there. But I still haven't jumped on to B2 yet, have I? Any kind of help me out? So this is probably important enough to report this statement, because here's kind of what I've got. So last map, H2. H2 of B2 equals H2 of X, which is my B3. And I seem to be stuck. Any ideas what I can do with that? I mean, it's this. Everybody agree with that? What can I do with that? I have to include about B2 minus X. Does anybody have the kernel of an idea on this? This is whatever it is, H3, H2. And what's the kernel of H2?
The image of H4.
Aha. So I don't know much, but I know that I can find there exists a B1 that goes to B2 minus X. Agreed? Now, what can I do again? This B1 here that goes to this difference, that comes from something up here, right? There's an A1 that goes to this, which goes to this. Can somebody tell me what the solution to my problem is here? If this pushes to Y, where does Y go? So A1 goes to B1, which goes to B2 minus X. So Y has to also go to B2 minus X. Everybody agree with that? Now tell me, what's the thing that goes to B2? See? It looks like it's, yes. Look at G of A2 plus Y. This is G2 of A2 plus G2 of Y. But G2 of A2 was X. And G2 of Y was B2 minus X. So G2. Everybody okay with it? Everybody understand the chase? Yes, this is often called a diagram chase. Any questions? Let's do the other result. Everybody got everything you need for this? Okay, same situation, except now we've got the bookend ones being 1, 1. Okay, so now let's suppose G1 and G3 are 1. Okay, we want to show that G2 is 1 to 1. So let's let's say A2 suppose you have A2 in the kernel G2. Our burden is so A2 is in the kernel. Our goal, our end game is more to show that A2 is 0. And that will establish that G2 is 1 to 1, right? Well, okay. The easy push this way is where does this go? Well, it's got to go to 0, right? Let's push this the other way. Here's A3. And that goes to 0, right? Because of the commutativity of the diagram. Now this time, what do I know about G3? Remember, bookend maps are 1 to 1. So if A3 goes to 0, what can I conclude about A3? It must be 0. Because of the fact it's 1. And now, what does that tell me about A2? So at this point, we've discovered because now I see that A2, shoot, it's going to 0. So it's in the kernel of F2, which is the image of F1. So there's something over here in A1 that goes to A2. Right up there. Now, let's chase around again. This goes to B1. And where does it go this way? It has to go to 0, right? Because A1 goes to A2, which goes to 0. That means this goes to some B one, and I don't know that B one must go to zero. What do I know about H one? H one is 1 to 1 also. So B one is 0. Well, what do I know about this map? It's 1 to 1. So A1 is 0 because the 1 to 1 is here. Therefore, what can we conclude about A2? So G2. Any questions on that? Notice we had to go to every point of that diagram to get one. Okay, any questions? All right, so let's see if I can get through something. Let's do the Hollywood squares here. This is often called the 3x3 lemma. Suppose we have a of our model morphisms. Maybe one, maybe two, three, 0, B1, B2, 3, 0, C1, C2, C3. With exact comments. So I'll assume that we have that diagram always has exact columns, so shorten that to right. A, if bottom two rows are exact, so the top row, and B, if top two rows are exact, so bottom. B is what I asked you to do in the homework. I will prove proof of the A. We'll use some good practice and homework here. Okay, so let me put a diagram here. See what we can get through. Nice. Okay. So. We're gonna prove A. I'm gonna do this mostly by picture, although like before, I'm gonna do, maybe record some key moments here. We're trying to prove that if the, bottom two rows are exact. Bottom two exact. Then so is the top, and remember the columns are exact as well. I'm trying to think from the start here. Yes, I think we'll start with the point here. We're recording this file. I'm gonna press F1, F2. One. Let's do, the kernel of F1 is, F1. One. Quoting the kernel of F1. We'll prove that. Well, let's let A1 be here. I hope I got that easy. Okay. I know that this is in the kernel, right? So A1 goes to 0. Agree? And of course, it's got to go to 0 here. All right, if I do the little box out. So far, so good. So A1 goes to some B1 here. And that B1 has to go to 0. Great. Well, what do I know about this map right here? Well, actually, cart front horse, what do I know about this map right here? It's 1 to 1, right? Because the bottom two rows are exact. So what does this force B1 to be? Must be 0, right? And what do I know about this vertical map here?
So 1 is 1.
It's also 1 to 1 because the columns are exact. So since this is 1 to 1 and it goes to 0, this must be 0. So A1 is 0. That was easy. Right? By the way, let me tell you, it always works out this way. The hardest part of this is going to be showing the last map is onto, right? For your homework problem, the onto one would be easy and the 1 to 1 would be hard, right? Because you're on the other side of the diagram. I promise you. Wait and see. Okay, 2. Let's show that the image of F1 is contained in the kernel vector. We'll do that containment first, and this is the image contained in the kernel is almost always pretty straightforward, right? Really, what you need to do is you just need to show that the composition of these two maps is 0. Agree? So let's start with A1. That goes to A2, which goes to A3. Now we need to show that A3 is 0, correct? Well, let's do the commutativity of the diagram. A1 goes here. And B1 goes here. And where does this go? Where does B2 then go?
Zero.
0. Okay. Because of the fact that this is exact, right? Because B2 is in the image of this source. Right? Now, how do we get that A3 is also 0? Actually, I probably should structure this a bit different. let me, before I get too carried away here. A1 goes to A2. And A2 goes to some B2 here. I'm gonna actually do it this way. A1 goes to A2, A2 goes to B2. Now, A1 goes to B1 here, and where does B1 go? Well, by the commutativity of the diagram, it has to go to B2. That's not that way there. So A1 goes here and here. So the B1 here has to go here. Now this has to go to 0 because of the fact that this is exact. And B2 is in the image of this. So A2 goes to B2, which goes to 0. A2 goes to A3, which goes to 0. Right? So A3 goes to 0 by, I guess I'll call this, I'll call this G3. But G3 is 1 to 1. So A3 is 0. And so image of F1 is contained in the kernel of F2. Because the composition. Any questions? All right, we've got two more things to do. We've got the other container. We need to show that the kernel F2 is contained in the image of F1. Okay. Next. This will probably be a little bit more than that one. So let's let A2 be in the kernel of F2. So what does that mean? That means that A2 goes to 0 over here in A3. Right? Now somehow I've got to show that there's something over here in A1 that goes to it. Well, the only thing that I can do really is kind of follow down here. So this goes to some B2. And this goes to 0, of course, because that's 0. So that means that B2 goes to 0. So B2 is in the kernel of this map. So what can I say? Remember, this row is exact. So if B2 is in the kernel of this map, it's in the image of this. So there's a B1 goes to B2. Okay. Now, I'd like to get back up here, right? Because remember, I've got to show that A2 is in the image of this map. At this point, I'm not sure I can get back up there, but I'm going to try. We'll try this way. Let me ask you this. If I push B2 on down here, what do I get? Remember, the columns are exact. And A2 pushes to B2, so when I push it again, I have to get 0. Everybody okay with that? Because B2 is in the image of A2, which is called the next map. So that means the B1 goes to some C1 that must go to 0, right? B1 goes to 0 this way, so it has to go to 0 that way. Well, what do I know about this map? So if C1 goes to 0, the C1 must have been there. So if I call this G1, what can I say? I can say that B1 in kernel well, it's in the kernel of this bottom half, whatever I call this. So it's in the image of G3 or image of G1. Right? Because B1 goes to 0, so it means it's in the image of G1. So there is an A1 that goes to B1. We're almost there. A1 goes to B1, which goes to B2, right? So A1 goes, I don't know it goes to A2, but A1 goes to X. And where does X go? Also, A1 goes to B2 this way, so it goes to X, which goes to B2. So what have I concluded here? This is G2. Notice that G2 is equal to G2 A2, isn't it? They both go to the same thing. Right? Because X goes to B2 and so does A2. Well, what do you know about G2? It's 1, 1. Is F1 of A1. So the kernel of F2 is continuous. Everybody cool so far? Dude, this was the worst one. I keep having to glue the stupid thing back together. Okay, here is fun part. Onto, and we're gonna take a little walk all over the place on this. So finally, we want to show F2 autonomy. Let's say A3 be an count. We got to get there somehow. This one is going to be the magic mystery. Okay, well, I mean, I don't know this is on to, so there's no way I can back it up. And lucky me, there's really only one way to go, and that's this thing. This goes to B for, right? And what do I know about this map? Well, this one right here is on. So there's a B2 that goes here. Well, what happens when I take B3 down here? I have to get 0, right? Because this is exact columns I follow the road down here. So that means when I go here and here, I'm going to 0, right? Because of the commutativity of the diagram. What does this mean? Well, C2 goes to 0. That means that there's C2 is in the kernel of this map, right? So it's in the image of this one. Right? So there's some C1 here. It goes to C2. What do I know about this one? This one is on to, right? So all the way down. Now, once again, there's no way I can pull back here, so I guess the only way I can go on this is forward. But there's no real reason to believe that this goes to my original B two, right? Nothing, so let me just say that this goes over here to X. But again, what happens to, where does X go when I push it this way? It goes to C2 this way, so it has to go to C2 this way. So X and B2, I'm gonna call this K2, I guess, this map. And I'm gonna notice that, let's call it, B2 minus X is in the kernel of K2, right? I agree with that. Which is, the image of G2. I agree. So there exists an A2 that goes to down here, B2 minus X. So where does B2 minus X go? This way. In B3. You know, tell me what happens. Well, let me ask you this, where does B2 go? I know where that goes. It goes to B3. Now you need to subtract off where X goes. Where does X go over there? Zero. X goes to 0, right? Because the middle row is exact. So in fact, this thing goes exactly B3. So A2 goes over here to some Y. And where does Y go? When I push it down. It also goes to B3. A2 goes to B2 minus X goes to B3. So this Y has to go to B3. So, what did I call this? G3. What do we have? We have G3 of A3 equals G3 of Y. Agree? Well, what do we know about G3? 21. And so, in conclusion to all this, what do we have? Well, notice that F2 of A2, bring a diagram here. F2 of A2 is Y when she pulls A3. So F2 is, do I see that? I feel like I should pass around the tip jar. Any questions? Diagram chases are a lot of fun. They're a little bit more pain to write up carefully, right? So I feel a little bit sorry for you in the homework. That's why I didn't assign, I don't think, too much. Right. So the next time we will get to, so I've already recorded snake lemma. we talked about this because it was one of the problem, or one of the homework problems at the beginning of class. It's in your notes. I won't go through, the description of this. We'll talk about, we'll move on next time, but you have to make sure you look at the snake lemma, and do it your homework. Any questions? Don't forget you got, homework due today, and if you got the time, I am going to derive the cubic formula of the math club. So it ought to be fun, because not only am I going to derive it kind of per principles, but I'll use it to find some interesting ideas. So a good time to do that by all. Other than that, y'all have a good weekend. We'll see you.